Hello, and welcome to TeachEngineering. My name is Ariana, and I'm currently a junior at the University of Colorado Boulder, studying to become a biomedical engineer. Bridges play a crucial role in our daily lives, connecting cities and facilitating transportation. Some bridges are simple and straightforward, while others are incredibly complex. Let's start with a question. What are some bridges you know that might be considered simple? You might think of a log over a creek or a small bridge over a stream. Now, what about more complicated bridges? Examples include the Golden Gate Bridge, or bridges that carry both highway and train traffic. What makes some bridges simple and others complex? Factors include their size, multiple purpose, environmental conditions, and material maintenance requirements. One amazing example of a bridge's contribution to connecting people to other populations and places is the Sky Gate Bridge in Japan, which connects to Kansai International Airport, located in Osaka Bay. When nearby airports in Osaka and Tokyo could not meet the demand, Japan took on the challenge of constructing Kansai International Airport on an artificial island. Spanning 3.7 kilometers, the Skygate Bridge is one of the longest truss bridges in the world, with an upper deck for vehicles and a lower deck for rail lines. Building such a bridge is not an easy feat. It requires careful planning and deep understanding of engineering principles. Have you ever wondered how engineers go about designing a bridge? Engineers start by understanding the problem completely. They ask questions like how strong does the bridge need to be, what materials should be used, how will the piers be anchored, what natural phenomena might the bridge need to withstand. Next, engineers determine the types of loads the bridge will carry, such as traffic from trains, trucks, bikes, people, and cars. They also consider environmental loads, like wind, hurricanes, tornadoes, snow, and earthquakes. After identifying the loads, engineers calculate the highest possible force the bridge might face by combining these loads in various scenarios. For example, a train crossing the bridge during an earthquake. Designing a bridge is not a simple task. It involves several steps of the engineering design process. The steps are understanding the problem, determining potential bridge loads, combining these loads to determine the highest potential load, and computing the material needed to resist that load. Let's start with understanding the problem. This step is crucial. If the engineering team doesn't fully grasp the purpose of the bridge, all their hard work might be in vain. For instance, designing a bridge for trains when it's actually meant for pedestrians and cyclists will be grossly inefficient and unnecessarily expensive. A clear understanding of the bridge purpose ensures the design is suitable, efficient, and economical. The next step is the load determination. Engineers consider three main types of loads. Dead loads. These are permanent loads, including the bridge weight and any other fixed objects like tolls, booths, or high-weight signs. Live loads. These are temporary and include things like cars, trucks, trains, or pedestrians. Environmental loads. These are due to weather or other environmental influences. Proper drainage is also crucial to prevent rainwater collection. Combining these loads is an important step in bridge design. Engineers use methods like the Uniform Building Code, UBC, and the American Society of Civil Engineers, ASCE methods to determine the highest load or the most critical effect for planning. The UBC defines 5 different load combinations such as 1. Dead load plus live load plus snow load. 2. Dead load plus live load plus wind load or earthquake load. 3. Dead load plus live load plus wind load plus snow load over 2. 4. dead load plus live load plus snow load plus wind load over 2. 5. Dead load plus live load plus snow load plus earthquake load. After identifying the highest load combination, engineers determine the size of the bridge members, like columns and beams, through detailed calculations. The stress due to a specific load is sigma equals force over area. Sometimes the area of the member is unknown, and hence the stress is unknown. Therefore, the use of the tensile and compressive strength of the member's material is used to size it. Engineers use the equation of force equals material strength times area. For columns, they calculated the area using the formula force equals material strength times area. Keeping units consistent is key here. Force in pounds and material strength in pounds per square inch. This results in an area measured in square inches. For beams, the calculation is a bit more complex. Consider the load at midspan and the beam's length. To calculate the size of a beam, the equation becomes force times length over 4, which equals Fy times Cx, with Cx being a coefficient related to the cross-sectional area dimensions. The best beam cross-section design often depends on the direction of bending. An I-shaped beam works well for one direction, while a hollow rectangular beam is ideal for 2 directions of movement. That wraps up our deep dive in the engineering process behind designing safe bridges. Next time you cross a bridge, you will have a greater appreciation for the meticulous planning and calculations that ensure its safety and reliability. To better understand bridges, look at the entire lesson on the Teaching Engineering website and check out the associated activity Loaded Up.